Okay, I think we're good. I think we're set. I think we're set. Are we all organized? I think so. Okay, so welcome everybody. Welcome to Astronomy Off Tap. This is our 30th episode, or our 30th event that we've had of Astronomy Off Tap Edinburgh. We have now had 8 of our different events offline since we've been dragged from our usual home, which is the pub and a nice cozy corner of Edinburgh, onto YouTube. So thank you so much for joining us. Thank you for coming along tonight. For anybody who hasn't been, it's Astronomy on Tap is a free event run by volunteers, which features accessible, engaging science presentations on topics ranging from planets to black holes to galaxies to the beginning of the universe. We have all kinds of different talks. The first Astronomy on Tap event was held in New York a few years back, and since has spread around the world. And Astronomy on Tap Edinburgh was started about 5 or 6 years ago by our founder, Amy Tyndall, and has gone on since there. So again, I know things are tough for everybody right now and that screens dominate everybody's days. So thank you so much for taking the time to come and join us. I know everybody's plans involved giving themselves a reward for being on their medium screens by staring at their big screens and scrolling through a tiny screen. So thank you for coming back onto your medium screen to join us tonight. It's really good to see you all. So tonight we're very lucky to have a couple of fantastic speakers who are going to be here to enlighten us with some fascinating astronomical topics. We'll also have, as we always do, some games and a little few updates from our rocket man Fred of what's happening in the night sky. As always, everybody is very, very welcome, and please do join in with your questions for our speakers. You can post them on Twitter, or you can add them into the comments on YouTube. You're very welcome to do that. You can also tweet us at AOT_EDI, and you can also find us on Facebook. If you enjoy tonight, please do subscribe on YouTube for future events and come along and see us. Or of course, you can follow us on Facebook and on Twitter as well. Okay, so I will start off our night with our first segment. So I'm going to pass this over to our rocket man, Fred, who's going to give us a bit of an update about what's happening in the night sky. So over to you, Fred.
Hey, John, I'm just going to share my screen. Okay, can you see that?
Yeah, that's great, Fred.
Cool. So, yeah, this is a quiet month in terms of rocket launches, but there's some cool things happening. So first up, on the 6th of January, it's really past, there's a Cygnus NG-14 is getting disposed of from the International Space Station. It's going to burn up in the atmosphere. And then on the same day, this is really past, but this is really cool. This is the BFR from SpaceX, which is their future interplanetary rocket, but they're testing the engines, the 1 second burn. And interestingly, this is serial number 9, so that's pretty cool. Right, and then there's a SpaceX Falcon 9 launching the Turksat 5A communication satellite. And this is on a souped-up rocket, which is pretty cool because you get increased performance and things. And then on the 10th, which is also past, Virgin Orbit's Launcher 1 is going to be launching. That's pretty cool as well. I think that's a second test demonstration. And then on the 14th of January, another SpaceX will be launching Transporter 1 rideshare with dozens of commercial satellites on. That's also a version 1.2 of Falcon 9. And then this one's not been slated yet. This is another SpaceX launch for the SpaceX Starlink broadband network, designated Starlink 16. It's also a version 1.2. Here's a comparison of some stuff that's pretty cool, because I mentioned the BFR, so you can see how big it is against the Saturn V, Statue of Liberty and things like that. And that concludes my slideshow.
Thank you very much, Fred. If anybody's interested, that noise you can hear in the background is because Fred is secretly orbiting Venus. It's a little known fact, but yeah, we're all volunteers, but we do get around. Yeah, so thank you ever so much, Fred. That was brilliant. So now we're going to move on to our first speaker of the evening, who is Rene Breton. Rene joins us. He received his PhD in physics from McGill University, Canada in 2009, and is a professor of astrophysics at the Jodrell Bank Centre for Astrophysics at the University of Manchester, and currently holds a prestigious European Research Council starter grant. His main research interests revolve around the study of pulsars, which we're going to talk about tonight, which he uses to attempt to understand matter under extreme density, gravity, and magnetic fields. Some of his past work enabled us to test geodetic spin precession, which I pronounced correctly, I'm very proud of, phenomenon predicted to exist in general relativity for the first time in strong gravity environment. And he also has a keen interest for science communication and co-funded the Pulsar Hunters, which is a citizen science project seeking to help from volunteers to find new pulsars. So Rene, welcome to Astronomy Off Tap, Edinburgh.
Hello there. I'm pleased to be here tonight. Let me just share my screen and get the presentation fired up. All right, so tonight in this short presentation, I'm going to try and convince you that pulsars are basically the most amazing astronomical objects in the universe. So you can see artistic depiction of pulsars. I particularly like to study the ones that are in binary systems. So that's why the ones you see, there's always another little guy next to it. So many of you probably have never heard about pulsars. They are some of the most extreme objects in the universe, probably next to black holes. They're tiny. We're talking about an object of a radius of 10 kilometers or so, but they're extremely compact. So a pulsar can contain something like 1.5 times the mass of the sun. So if you imagine all that mass that makes up the sun, but even more than that, but all shrunk down to the size of a city. So on average, the density of a pulsar is just as large as the density of atomic nuclei. And to give you a comparison, if you were to take every single human being on Earth and shrink them, you would have to shrink all of us down to about the size of a dice in order to get a comparable density to that of pulsars. So extremely dense objects. They have large gravity as a result, but also they spin really fast. So when these objects are born, they're born from massive stars that are something like 8 to 10 times the mass of the sun originally, or even bigger. And then at the end of the life of the star, which grows as a supergiant, as we call, the star explodes, and it turns into the explosion, we call it a supernova. So it leaves behind like a sort of cloud of gas, which we call the remnant, the supernova remnant. But at the center of it lies the core of the star, which is where the nuclear reactions used to take place. And that core shrinks down to the 10-kilometer radius, as I was talking about. So by this process of like shrinking, the star spins really quickly. So we're talking about rotation periods between something like 1 millisecond to 10 seconds for most of them. They're also extremely powerful magnets. So the magnetic field of a pulsar, a bit like the Earth's magnetic field, has a North Pole and a South Pole, except that the field strength is something like 1,000 billion times the Earth's magnetic field. So don't carry on your keys or any spare change in your pockets if you go on a pulsar, because you'll be dragged down to the surface real quick. The way we see them is through what we call the lighthouse effect. And it's because most of the light that they emit is actually produced along beams which are in line with the magnetic field. So most of the light is not emitted in all directions, but more in a focalized way through these emission cones. So as the star rotates, basically, you see this cone of light sweeping across your sightline. So that's Edinburgh, where we would be in principle if there was no COVID. And you can see basically the relative size of a pulsar. So basically it would more or less encompass the entire core of Edinburgh down to the ring road. And they basically rotate faster than a kitchen blender. So observing pulsars can be difficult in the optical with visible light. because they're very faint. They don't emit a lot of optical light. So the image you see is that of a pulsar nebula. That's called the Crab Nebula. And at the very center, you can see two little dots. And actually, if you take very, very quick optical images, you can see one of the dots blinking. And it actually blinks 33 times per second. But in fact, most pulsars, you don't see them in the optical at all. They're way too faint. But they tend to emit a lot of radio light, however. So, so to see them, we typically use radio telescopes, such as my favorite, the one that's behind me on the picture there, the Lovell telescope at Joddo Bank, just south of Manchester in Cheshire. And perhaps you don't know that, but optical telescopes, they obviously have CCD cameras with a lot of pixels, and they can take really beautiful images of the sky. But typical radio telescopes like the Lovell, they are basically 1 pixel cameras. So essentially you get only the light from one single location in the sky, and you cannot make an image. You need like a group of telescopes to do that. So what we detect from the pulsar is more or less like the sound or the light intensity it produces rather than an actual image. So we see our charts basically or time series of noise over which is superimposed the heartbeat of the pulsar every time it flashes. And that's what we observe. They spin extremely fast, but also extremely regularly. So if you were to observe it and then stop observing for a little while and then resume the observation, if you know exactly the rate at which it rotates, you can actually pick it up later on and predict exactly when the next heartbeat would come. And that you can actually do where the gap, could be separated by months. So, so they're extremely, extremely stable rotators. Because we see them in the radio, we can think of them as basically listening to them, a bit like we listen to music over the radio waves. So let me play a couple of pulsar sounds to just give you an idea of what they sound like. So the one you can hear now, hopefully, is called 0329. This is one of the brightest pulsars in the sky. So this one, we don't really need to amplify the sound actually, because that's how it would sound if we were literally connecting speaker boxes to the Lovell telescope. So the rotational period is about 0.7 seconds. Now, let me play this one. So this one is rather annoying because it's basically a few milliseconds for one rotation. So all you can hear is the sort of like modulation of the intensity over time, but you don't hear individual rotations. Then this one, this is the pulse. And you can hear actually the two tones. Right? So the typical heartbeat of that pulsar is made of a high peak and a smaller peak. And as I played it, you could hear like this sort of like the major peak followed by the smaller one, this sort of like tuck, 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 tuck. And I believe the next one is even more of this in terms of the structure of that pulsation. And finally, this one. This one is really annoying to listen to. It used to be the fastest known pulsars at 682 rotations per second. And now, well, from 1981 until 2006. And at that point, we discovered the current record holder, which is 714 rotations per second. So listening to that obviously could drive someone completely crazy, and you can imagine that astronomers, we actually don't listen to the sound of pulsars, so it's just for show, for public talks, because usually we just look at this sort of like cardiogram type of graph. So what do we do with pulsars? Well, we look at them, we measure the time it takes to rotate, and it enables us to do a lot of really cool science. And I'll just give you one single example here, but you can ask questions about what else we do with them. Often we link up the Joddo Bank telescope, the Lovell, along with 4 other ones across Europe, one in the Netherlands, another one in Germany, one in France, and one in Sardinia, in Italy. And by linking them together, we basically have the equivalent of a much bigger dish, more sensitive, so we can measure the rotation even more accurately. So one thing we are interested in is actually detecting colliding black holes and other compact objects. So there are black holes in our galaxies that are basically binary black holes. So you have two stars that exploded and they were connected together by gravity. So they were orbiting each other in the past. And the binary system has survived the explosion. And so eventually black holes will end up colliding because their orbit actually dissipates energy through what we call gravitational waves. So basically the motion of the stars ripples space-time and it dissipates energy, and that energy comes from the orbit. So when the big collision happens, you have this sort of very intense ripple in space-time that's produced, a bit like if you were to drop a pebble in water. And as a result, you have this wave that propagates, and when it goes through Earth, essentially it changes the physical dimension, literally, of space-time. So it basically makes the Earth and us as well, and atoms, kind of jiggle, a bit like you can see in the video. Except that the jiggling is basically of the order of a thousandth of the size of a proton. So it's really, really, really tiny. Nevertheless, that sort of change in space-time has actually been measured using super accurate lasers, using an experiment that's called LIGO. So they detected basically the ripples in space-time using lasers. And so that's really amazing. It was one of the greatest discovery of the century so far. And using these Earth-based gravitational wave detectors, we can basically detect stellar-sized black holes that collide, or even neutron stars, pulsars, basically, that collide. However, we can use the heartbeat of pulsars essentially as a GPS. So if we have many in space, as you can see on the picture, you can basically use the frequency of these pulsars to triangulate your location and your velocity. And basically, if a giant gravitational waves passes through Earth, then we can measure the relative change in position of Earth compared to these pulsars. And the types of gravitational waves we can detect that are more like supermassive black holes. So if you have colliding galaxies, the galactic black holes at the center that are millions of times the mass of the sun can then interact, collide, and these sort of gravitational waves are the ones that we can detect from space using pulsars. So that's just one of many examples of the sort of things we're trying to achieve with pulsars. That's it for me.
Okay, fantastic. Thank you so much, Rene. That was a brilliant talk. We really appreciate you coming along. And if you don't mind, we have a few questions from our learned audience that I hope you don't mind us putting to you, if that's okay.
Absolutely.
Okay, so the first question I think was from our audience asking us, how many pulsars do we currently know of?
We know about 3,000 pulsars so far. So the numbers keep increasing. We believe that our galaxy contains something like 20,000 to 100,000 pulsars that we could detect, right? So the object, the spinning object might be there, but it could be that the beam, right, this sort of lighthouse beam actually does not intersect our line of sight, right, as it rotates. So there's probably 10 times more pulsars in our galaxy, but we just cannot detect them. So the real number of these objects is probably somewhere between 100,000 and maybe 1 million, but only maybe 10% of them we can ever detect. So we're at 3,000, and in a couple of years, when a new telescope called the Square Kilometer Array will start operating, so by 2030 at the latest, we believe that we might be able to detect every single one in our galaxy.
Oh, fantastic. And the second question we have was, so why are pulsars useful? Like, what do we learn from this, and how can we use that information?
Yeah, that's a really good question. So, well, the object, as I hope I've convinced you, are extreme, right? So the density itself is comparable to that of like the core of an atom, right? Not the entire atom with the electrons that orbit really far, but like literally the nucleus. So a pulsar is literally like a macroscopic atom, right? The size of a city. And so one of the questions is what happens to matter when you pack so much of it at such large scale. And for over 50 years, we've had theories about what the internal composition of pulsars are. So we believe there are neutron stars, so they're basically at such extreme densities. Even the protons cannot sustain the immense pressure, so they turn into neutrons. So you have this soup of neutrons. But we think that at the center, there might be more exotic particles. So it could be that the neutrons break apart and then turn into the fundamental particles that make them, which we call the quarks. But there could also be other weird exotic particles like iprons or other matter that we don't really understand. So by studying pulsars, we obviously we only have access to what we see from the outside, but if we measure things like the radius and mass of pulsars, then we can actually work out or try and work out what's going on inside. Another application is to use pulsars basically as tools. So they spin really fast. To give you an idea, the surface of a pulsar, you would be, if you were to be able to hold on there, you would basically go at about 15% the speed of light. So all these effects are, so super extreme. And like you mentioned, in my biography at the start, so we can use the motion of pulsars, like their orbit, which we can measure extremely accurately because of the, essentially the flash that they produce. And we can measure the orbit and compare to the prediction of relativity, which is an even better theory than Newton's theory to predict the motion. But then if Einstein's theory was not correct, right, it could break down when, in the solar system, it might still work because things are not too extreme. But around a pulsar, it may be so extreme that it breaks down. And maybe another theory would explain the results we observe, whereas Einstein's would not work. So we can do these sort of things, for instance.
Fantastic, thank you. That's brilliant. So just a couple more questions for you. Are there any other interesting sort of phenomena that we know about when pulsars collide with something else, like apart from gravitational waves?
Yeah, for sure. So it turns out, so when we detected the first gravitational waves with LIGO, the sort of laser experiment I showed the image for, they were black holes that collided. But then about 2 years, I think, or 1 year later, the first discovery, then 2 neutron stars were actually observed to merge. And it turns out that this phenomenon also produced a really intense flash of actual light. So not just, black holes, they're dark, right? We don't see them. So there was so far we haven't seen any flash. But when neutron stars collide, pulsars basically, they do produce a flash of light, which you can see like basically an increase in optical light, and then it fades away. And it looks like some kind of a nova or mini supernova, if you want, a redder nova. But also there's radio light that's emitted, but mostly there's very intense light producing gamma rays and X-rays. And you see literally a flash which lasts something like a second of X-ray and gamma ray light. And those we call the gamma ray bursts. And they've been observed for something like 40 odd years now, and or even more perhaps. And there are 2 types of these gamma ray bursts. There's the short duration gamma ray bursts and the long duration. And the short duration gamma ray bursts, it turns out that they are neutron stars that merge. Whereas the long duration ones, they're probably related more to like supermassive stars that explode. So it was hypothesized for a long time. People would observe these bursts, in distant galaxies. Didn't quite know what they were, but suspected that they could be merging neutron stars. And then when the first double neutron star merged, and that we observed with LIGO, we saw the flash at exactly the same time, basically.
Fantastic. Okay, brilliant. Thank you. The only last question, just with regards to merging pulsars, we're 100% sure that it's not just a Norse god making hammers in the sky out of neutron stars. We're sure that's not the reason, right?
Yeah, we're pretty sure now. Otherwise, it would have to be really clever. But as a small joke, when Jocelyn Bell found the first pulsar, right, and then reported to her supervisor Anthony Hewish, they were a bit worried for a little while that it might be some sort of aliens trying to contact us. But as it turns out, we can measure the distance to pulsars, and also they're all over the sky. So then it was clear that there were not aliens in orbit just about to attack us or anything, and around Earth, and they're far away. So so it's pretty clear that they are stellar objects, and they're not people or mythical superheroes. Yeah.
Oh, not chatty aliens. That's good to hear. And then the only other thing I wanted to ask is that obviously, as a founder of the Pulsar Hunters, if any of our viewers would like to become a Pulsar Hunter, is there a way that they can do that?
Yeah, of course. They can go to pulsarhunters.org. You can also access via the website of the Zooniverse, right? So ZOOniverse.org. Currently, the Pulsar Hunter is actually down because we don't have any data for people to look at. We're hoping to source some in the future, but people can contribute to citizen science projects like trying to detect distorted images, lenses that are produced from the distortion of light, depending of light by clusters or all kinds of other things. So there's a lot of really fun projects there. So have a look at Zooniverse. We definitely recommend.
Thank you so much. We'll get it up on our Twitter feed so everybody can have a look and hopefully join in and find out more. So, but yeah, thank you so much, Rene, for joining us tonight. That was a really, really interesting talk and a lot learned about pulsars. So thank you so much for joining us.
Thanks a lot. Fantastic.
Thank you.
Cheers.
Okay, so we have our first talk for the evening now. So we're going to move on to our first game of the evening, which is going to be run by our games master tonight, which is Erica. So Erica, I believe you're using a couple of the volunteers as part of this game. So I will hand over to you, and I will disappear.
Yep, thanks, John. I have to say, I have this fear that my mom is going to FaceTime right in the middle of this, because she always seems to know when I'm on a Zoom call, and then she FaceTimes and it has that really annoying chime. But if that happens, we'll just roll with it because it'll be funny. Maybe we'll answer her, ask her what she's having for dinner. Today's game doesn't have a name. I should have given it a name, but we're going to have a little bit of fun with Fred and Shinran. So I'm going to turn my camera off and spotlight them, and then I'm going to share my screen. So fingers crossed that this goes well and there's no FaceTime call to interrupt it. So stopping the video now, and we'll just share, we'll add Fred and we'll add Shinran. Everybody say hi to Fred and Shinran. Shinran and Fred say hi to everybody.
Hello.
Hi.
Right. Okay. So now we'll try the difficult part, the sharing of the screen part. And somebody shout at me if you can't see my screen. I bet you can see my YouTube. Okay. So Fred and Shinran, welcome to the game with no name. For this game, you will need to tell us the definition of the word. You'll each get 5 chances, and whoever has the most at the end will win. Okay?
Okay, sounds good.
Okay, so Shinran, we're going to start with you. Please, can you tell me what is a maelstrom?
Some kind of epic storm?
Well, if you can see my screen, you can see that you have 3 choices. A powerful, often violent whirlpool sucking in objects of a certain radius, a powerful, often violent storm around a black hole, or a powerful, often violent electromagnetic.
I see how the game goes. I'm going to choose C, a powerful, often violent electromagnetic wind.
And you would be wrong. The correct answer, Fred, for the steal is... Say it a little bit louder, Fred. Number 1 is correct. A powerful, often violent whirlpool is sucking in objects of a certain radius. Shinran, this is not a great performance.
Yeah.
All right. So for the next one, we'll go on to Fred. On to slide number 2. Sorry, whoops. A planum. Can you please tell me what a planum is?
I would say number 2.
A high plain or a plateau? Is that your final answer?
Yes.
And you would be correct. So far, 2-0 Jinran. A chance to redeem yourself here. Number 3, absolute magnitude. Give you a second to read the definitions. I assume you can see them.
Yeah, those are pretty long definitions. You want to read them out so that the audience can see it?
So, can the audience not see my screen?
No, they can. I'm just trying to be lazy and not read myself.
Oh, well, I can definitely read them out for those of us who are lazy. Is absolute magnitude a scale for measuring the actual size of a celestial object without accounting for the distance of the object, the actual brightness of a celestial object without accounting for the distance of the object, or the actual distance of a celestial object?
No, I'm going to go with brightness. Maybe that's not correct. I'm going to go with B2.
You're going to go with B2, and you would be correct. Yeah. Coming back, absolute brightness. Well done. Okay, so now we jump over to Fred. Fred, what is ejecta? I'm trying to say this with a straight face now.
Okay, number 1.
You think that ejecta, and honestly, if you know all of these terms because you've been studying the dictionary, is material that is beneath the surface of a body such as a moon or a planet that is ejected by an impact and distributed around the surface. You would be correct. I know, Jinran, it's not great, is it? It's not looking good for you, my friend. 3-1. Yeah. Jinran, look, that's all right. You have a chance here. We're going to bring you back to the right ascension. What would be the right ascension? Do you want me to read them?
No, it's okay. I really not sure. So I'm just gonna go with 1. 1 in 3 chance of being right there.
Yes, probability was not in your favor because the correct
is really when you go for that.
Do you want to take a second guess? No points for the second guess, though.
No, I'll hand it over to Fred for that.
Okay, Fred. I bet you know what this is. I don't think I knew how much you knew about space, Fred.
I think that's number 3.
Yes, but you're also incorrect. The correct answer is number 2, the amount of time that passes between the rising of Aries and another celestial object. Okay.
I feel like Fred still lost the point there since he had a much better odds than I did, and he still didn't get it right.
I mean, that's a very interesting argument, but I'm not going to pass judgment on that. So, Jinran, back to you. The planemo. I probably totally said that wrong. It's probably like planemo or something like that. But what is a planemo?
Oh, is it a large planet or planetary body that does not orbit a star?
It is. Congratulations. You have that one correct. And I've totally lost track of the scores at this point. What is it?
2-3.
2-3. Okay. So Fred, back to you. A cache. Do we lose Fred? You're still there. There you are. A collection of items that is stored in the accessible place. Incorrect. Jinran, it's your chance to tie.
Okay. Okay, that's a tough one. I realize a long pause is not really great for live broadcast, so I'm just gonna randomly choose 3.
Oh, come on, Jinran, you were so close to coming back. The correct answer is 2, a collection of items of the same type stored in a hidden or inaccessible location. And I like how you're like, nobody cares about a long pause on YouTube because it's so boring, but they're all staring at it too and thinking. Either that or they're looking at you saying, why didn't you know what this is?
Fair, since Fred also didn't get the 50-50 one, so that was fair.
Right, so our scores are still 3-2, and Jinran, we're back to you with a synodic period. Also, I feel like I should get some extra points for my clever definitions here. Just remember that the name of this show is Astronomy on Tap.
Oh, very good.
Not that I'm offering any hints whatsoever.
Now I feel extra bad if I get it wrong now. Is it?
You should.
Is it 1 for wavelength? Oh,
Oh,
no.
come on, Jinrod.
Oh, no, I knew I got that incorrect.
Fred, want to steal?
Yeah, I'd say number 3.
You would be correct, Fred, widening the scores from 3-2 to 4-2. I'm starting to realize that this game might be a little long, but 2 slides left. No problem.
I'm aiming to go for a late surge. That was my plan all along.
Well, then you better hope that Fred gets this one wrong because it's his turn. Fred, the Planetia.
Number 1.
No, Fred, that is incorrect.
3.
Say that, Jinron?
3.
It is correct. Number 3. Bringing it closer.
Begins. The late
4-3. And the next one is yours, the prograde orbit.
Ooh. Okay.
If you get this one right, you could tie it.
Okay.
And then I'll have to use my tiebreaker slides because I did create those.
I feel like, since I actually work in physics, I might lose my job tomorrow if I keep on getting these wrong.
Yes, because this is broadcast
I don't work.
to YouTube and everyone can see it.
Yeah, I think YouTube might just accidentally go down. No, I'm only. Okay. Prograde.
Just think what the opposite of prograde might be.
I see your point there. Is it 3?
It is indeed 3. You've tied it. I get to use my tie slides.
You just did that because you want to use your tie slide.
I do. And in fact, I'm going to use my tie slide, the last slide here, the Terminator. Fred, can you tell us what is a Terminator?
2 and 3.
2 and 3.
I feel like that's cheating somehow.
It's also wrong. Shinron, what is a Terminator?
It must be 1 then in that case, surely.
It is correct. It is 1.
The late surge. I told you.
The late surge. And Shinron comes to win. I hope for all the people that were playing along at home, they weren't nearly as bored as I was, and that they Googled as furiously as I just did to remember the definitions of each of those terms. And I am now going to stop and hand back over to John.
Thank you very much, Erica, and thank you so much to Fred and to Jinran for being our guinea pigs. I've seen many complex PowerPoint definition games on YouTube, but that was the most exhilarating. So it's good to see. Okay, so we are now going on to our second and final talk of the evening, which was with Romeel Dave, who has kindly joined us as well. So Romeel is a professor of physics and astronomy at the University of Edinburgh. He was born in California and grew up mostly in the US with some early years in India. He got his bachelor's from Berkeley, which should be Berkeley, but we won't get into that, a master's from Caltech, and a PhD in astronomy and astrophysics from Santa Cruz. He held a Spitzer postdoctoral fellowship at Princeton, a Hubble fellowship at the University of Arizona, and then spent 9 years as faculty at Arizona and 5 years in Cape Town, South Africa in 2013, before finally ending up at Edinburgh in 2017. So I'll welcome Romeel to the event, and I shall pass over to you.
Awesome. Hi, everyone. Can you see me? I hope you can.
Yeah, I can see you well.
Excellent. All right. So yeah, after that rousing comeback victory by Jinran, I hope this one will be just as suspenseful and exciting, because we're going to do a little murder mystery theater right here. Okay. So the subject in question is a poor unfortunate galaxy that goes by the name of M87. And I'm going to start my PowerPoint here, and we can get on to the story. Da, da, da. Galaxy Murder Mystery Theater. Okay, the case of M87. All right, so what's going on with this thing? So, as most of you know, galaxies are collections of stars. You know, like for instance, our Milky Way is the galaxy that's our home. That's our home. And galaxies are kind of like people. They're born, they live. Actually, they're more like crocodiles because as long as they're living, they're growing, right? And then they die. And when they die, they stop forming any stars. And the real question is, and it's one of the important questions in astronomy today, is why do galaxies die? All right. And in particular, we're going to look at this one galaxy called M87, for which we might have some pretty nice clues because it happened to be one of the closest big dead galaxies that we see. And we're going to try to sort out what might have killed M87. Okay, so let's get on with it. Here we go. Here's a picture of a galaxy, right? So you probably have all seen, if you think of a galaxy, you might think of something like this. This one is not M87. This is a nice, healthy, live galaxy called M101. So it's the 101st object in a catalog from Messier back a long time ago. And you can tell that it's alive. Why can you tell that it's alive? Because it turns out that when you have young stars that are just newly formed, they're quite blue. Okay, they look quite blue. And you can see that there's all these spiral arms in the galaxy, right? So there's this redder thing in the center, maybe where some of the old galaxies, first formed. But then the galaxy is continuing to grow using these in these spiral arms with all these new star formation. Now, what is driving the star formation? Well, what's driving the star formation is cold gas. Okay, so as long as you have cold gas around, it collapses down. It's like gravity brings it all together and eventually forms into a protoplanetary disk, out of which you form a star and so on and so forth. And that's going on a scale that's much, much smaller than this picture. This picture contains, something like this galaxy M101 is pretty similar in many ways to our own Milky Way, has probably a few hundred billion stars, and is quite rich in gas. And you can actually see the gas. I'm overlaying here an image in the infrared. Okay, so if you look at the infrared, you can actually directly see the gas instead of the stars, and you can see how this infrared, the gas, the green part is tracing out this spiral structure. So that's an example of what a nice, healthy galaxy looks like, right? Here's another galaxy, and here's our poor victim in question. All right, this galaxy looks a lot different. All right, doesn't have any spiral arms. You notice that there's no blue parts in this galaxy at all. Right? It's dead. It's not forming any stars. In fact, it hasn't been forming stars for something like 8 or 10 billion years. And remember, the universe is only about 14 billion years old. Yet, despite the fact that it has this huge collection of stars, hasn't been forming stars in a long time, it's actually about 10 times, there are about 10 times more stars in M87 than in M101. So apparently what happened is a while ago, early in the universe, this galaxy formed a huge number of stars. And then, for some reason, it decided, I'm done. I'm dead. Okay? Now, the question becomes, why? Why did it decide to all of a sudden stop forming stars? It seemed like a nice, healthy spiral, could keep going, right? What killed M87? All right. So, we're going to try to go through this, all right? And the first thing, of course, when you have a murder mystery is you try to round up some suspects. Okay, we got to round up some suspects of what might have killed M87. So this is one of the first suspects they thought of. Maybe it just happens that M87 had a bunch of cold gas, right? And eventually just formed it all into stars, and then that was the end of it, right? And just kind of ran out of gas. And once it runs out of gas, you run out of fuel and you're done, right? Well, that seemed okay at the time. But eventually it was realized that you might be surprised to know that when you look at an image of a galaxy, of a piece of the sky, right? You see a lot of you see a few galaxies in there, but you see a lot of empty space. Turns out that empty space isn't actually that empty. There's this stuff in between galaxies called the intergalactic medium, and it's filled with hydrogen and helium, a lot of the fuel that you need to form things like the sun. The sun is about 70% by mass hydrogen, about 28% by mass helium. So as long as there's all this gas around, and of course gravity is always working, right? You can't stop gravity, right? So gravity is always pulling it in. So that must mean that this gas is being brought into this galaxy all the time, right? So there should be plenty of cool gas. And in fact, you can work out the timescales for this. It's quite fast, right? So the galaxy, something like M87 is so massive that it should just be bringing in gas like gangbusters, right? It's got so much gravity, it should just be pulling in gas like nobody's business. But it's clearly not. Or at least something is, it's certainly not, that gas maybe is not cold, right? So another idea that people started thinking about is maybe M87 died in a big car crash, right? So sometimes, every once in a while, galaxies run into each other, all right? Happens fairly rarely, but in fact, you can see examples of all of this over the sky. So what's shown in this little montage here of 6 images down at the bottom is a series of images where these are actual galaxy pairs on the sky, taken with the Hubble Space Telescope, but they're arranged kind of in a sequence of how we think galaxies undergo mergers. So you start off with sort of 2 disky galaxies, they come closer and closer together, finally they start actually interacting with each other, they turn into a big giant mess, and all at the end, kind of all the spiral structure is gone and you end up with a big blob. And people went, aha, maybe that same thing that turned these spirals into a big blob happened to M87. There were 2 galaxies smashed together and you left with a big blob, okay? And in fact, this is what we think is going to happen to our own Milky Way and Andromeda in about 4 or 5 billion years, all right? So maybe something about that big smash up kind of got rid of all the gas, and flared it up and somehow ended up with no gas left. But we have the same basic problem, right? It turns out you can temporarily kill galaxies like that, but not for very long. And we know that M87 has been dead for more than 8 billion years. So, eventually gravity is going to bring in all this gas from the intergalactic medium and you've got the same problem. So these suspects didn't seem very good. So it actually was only about 15 years ago that people started thinking, what the hell could it be? So to understand that and to kind of go into this, sometimes if there's nothing obvious, right, it's like Sherlock says, right, if you rule out everything that's however improbable, or rule out all the things that are impossible, whatever's left, however improbable, must be the truth. So let's take a look at this image of this galaxy. Now, this galaxy just looks like a big blob of stars. This is M87 again. But let's play a little bit with the contrast. Let's add in some infrared data. So this is this is sort of near infrared data. And let's take a look at this galaxy again. Okay, so this is another image, exact same galaxy, right? But now, take a look at that little blue streak that's coming out of the center there. Or is it coming out or is it going in? We don't even know at this point, right? That's weird, right? It doesn't even show up in the optical image. What the heck is that? Can we zoom in on that a little bit? Well, like Rene says, when you put telescopes far apart, like you can with radio telescopes, and take a very deep image of it, now zooming in right in on that little blue thing, this is what it looks like. So this is what it looks like in the radio, again, using these multiple telescopes in multiple countries to sort of piece together a very high resolution image. Whoa, check this out. It's coming from way down in the center of a galaxy. And it turns out that this bright blob, they can actually trace that over time. Like they've measured it at different years and they see it's moving outwards, right? And because, this thing is pretty far away, right? And the fact that they can see it move tells you it's moving really fast. And so this is actually a jet of material coming out at relativistic speeds, right? You can see it if you step back in the radio and try to take a bigger image and try to get more sensitivity to diffuse stuff. Whoa, check that out. Look at how this radio emission is from this jet is actually going out. So this jet appears to be going out, hitting whatever intergalactic medium is out there, kind of dissipating out there and depositing all this energy, right? This energy that's coming out, this is synchrotron emission. This is very high energy emission. You can also see it in the X-rays. So if you take an X-ray image of this thing, this is what it looks like. Now we can only see the jet coming out of one side. Maybe the jet on the other side is obscured for whatever reason, or it's it was active before but not now. No one quite understands, but it's very clear that whatever is putting out this incredible jet from the center of the galaxy at near the speed of light is clearly doing huge things on immense scales. Now think about it, right? If we go back to this image, right, think about the size of this thing. The galaxy itself is much smaller than this jet. So the galaxy is actually a pretty small thing on some of these images. This is affecting things at hundreds of thousands of light years away, these relativistic jets. Now, what the heck could be causing this relativistic jet, right? Well, here we go, right? We're kind of zoning in on the perp here, all right? We're gonna get him here. All right, how can we look at it? Well, we can look, it turns out, at higher and higher resolution, not only with VLBI. So again, on the upper left one, it shows this image, this radio image of M87 again. And the upper right, I've just overlaid the radio image with the optical image just to size, to show you how big the actual galaxy is compared to how long and extended. It extends way beyond the galaxy, right? So you see this jet coming out, right? And you can zoom in further and further to the center of the jet. And if you remember, a couple of years ago, actually was it last year? Well, a couple of years ago now, the Event Horizon Telescope imaged for the first time a black hole, right? They actually got an image of a black hole using this telescope that basically spanned the entire Earth. Again, this idea of using interferometry, multiple dishes all over the Earth. That's that bottom image here. And that is where the jet is coming from. Now, of course, you can't see the black hole itself. The black hole is black. It's the hole in the middle, but you can see the accretion disk around the black hole, right, due to general relativistic effects. So this jet is coming from this central black hole. All right, now that's got to be a clue. All right, so we're zoning in on it. And what seems to be happening here is this jet is coming out of this black hole. It's going on to very large scales, and it's heating the gas around M87. So here's sort of the second part of the story, right, which is the space around M87 is filled with gas, but this gas has all been heated up because of this jet, because of the energetic output of this black hole. You can see the hot X-ray emitting gas sort of in purple in this image. That's the M87. It's very, very tiny on this particular plot. You can see the little X-ray jet out there. And you can see on much larger scales, there's all this remnant jet energy that's been deposited there, right? And essentially what happens is, as we know, hot gas cannot form stars. You need cold gas. So slowly, over billions of years, the energy from this jet heats all that gas. It can't form stars anymore, and M87 dies. Da, da, da. So this is actually how we think these large elliptical galaxies end up dead. It's kind of almost suicide. During the time that they're growing, not only are they growing their stars, the cosmic garbage dump, if you want, at the center of the black hole continues to be growing until it gets so big that the energy released from that black hole actually suffocates the galaxy itself, right? So this is essentially the solution of what we think the solution is, or at least along the right line to how galaxies kill themselves. So this is kind of part of the whole life cycle of galaxies, where galaxies are born sort of small and irregular. They grow through a spiral phase, and eventually this black hole gets big enough to essentially self-starve, if you want to think about it. And that's it. That's how M87 died. All right, and I'll stop there.
Thank you very, very much, Romeel. I will let you know that we did have during that talk a series of comments trying to guess what was killing off galaxies, and we had a range of comments. I believe the Death Star, Dr. Manhattan, a leftover sandwich. There were several guesses. Some were good.
I couldn't go through all the ideas, but yeah, those, scientists take those very, very seriously, and we're able to rule them out through a systematic experiment, I have to say.
Fantastic. Oh, thank you. That was a really, really engaging and exciting way of looking at this. We did have a few events ago someone to come on to talk about M87 and about the picture of the black hole. I think it's something we had loads of people really interested in, because it created such a stir, I think, in the media of this thing, this kind of anomaly that was only existed in popular imagination, and then suddenly there was a picture of it, and I think it just captured so many people's imaginations to say, like, well, this is what we've been talking about all these years.
Yeah.
I've got a few questions for you, if that's okay with you.
Yeah, sure.
So just in terms of when we look at this, as we think about sort of galaxy death and black holes, are there any sort of predictive indicators that we can find that might say, well, this is starting? Is it that we'd have to look at a galaxy for a long period of time to see some of these patterns emerging, and then we can predict that it is going to eventually go the same way, or is it something that's more random?
Yeah, so that's a good question. People are looking for smoking guns, observationally. And the big problem is sort of, you think about it, what is it doing? It's like the galaxy is laying siege to itself, right? It's basically heating up everything around it and stopping its flow. So the problem is it's not like simultaneous, right? It's sort of like you put out the energy, then you have to wait a while. Meanwhile, the galaxy is like going along doing its thing, and then eventually it finds, oh, I've run out. So it's hard to find this sort of coeval smoking gun type signatures for this. Instead, what we often try to do is build models of galaxies, so galaxy formation models, and that's what I actually do in my real life, is to try to build these kind of galaxy evolution models and include these kind of processes and say, okay, if we include this type of thing like black hole jets into our models, do we now see the galaxy population coming out of our models that looks like the real universe? And the answer is, essentially for the last 5 to 7 years, people have been doing this, including our group. And the answer seems to be unequivocally yes. You basically have to have this process going on. That's the only within a cosmological context to actually produce a population of things that look like M87, which are, pretty common.
Fantastic, thank you. It's a really good explanation. Another question we had was that somebody asked on our YouTube feed that they heard that most galaxies have black holes in their centers. Is this the destiny for all galaxies? Do we think this is sort of a fait accompli, that all of these going to end up eventually like this?
As far as I could tell, I think that's true. I mean, the only thing is the black holes do have to get a certain size in order to be able to have enough energy output to actually kill the galaxy. And the galaxy could get killed before that due to things like dark energy accelerating the expansion of the universe, and that just starves the galaxy outright. So it may not have to do with the black hole in that case, but I think for anything in the next, anything certainly in the past and in the reasonable future, we expect that is kind of how galaxies are going to die, and that will probably be the fate of the Milky Way in 4 or 5 billion years. We're going to merge with Andromeda. We're going to turn into elliptical. We're going to form a much bigger black hole during that process, and once that happens, we can start the cycle basically, and over a few billion years, probably we'll end up, the Milkomeda remnant of that merger will end up like M87, killed by its own black hole.
Fascinating. A couple more questions for you as well. For M87, just how far away is it from us? Like, it's not next door, I assume, but it is. How far is it away in galactic terms?
Yeah. So I mean, so it's the largest galaxy in the Virgo cluster of galaxies, which is the nearest sort of reasonable sized cluster of galaxies. It's something like 50 million light years away, give or take. So maybe I can't remember exactly, but I think it's around 50 million light years away. So it's pretty far away. I mean, for scale, the Andromeda galaxy, which is our nearest big galaxy, is something like 2 million light years away. So it's farther than that, but not that much farther. In astronomical terms. So yeah, that's where it is. It's about 50 million light years away, and it's surrounded by a whole bunch of other galaxies. It's in a cluster of galaxies, and it's what we call a brightest cluster galaxy.
Fantastic. And then final question for you is just after a galaxy dies and sort of remains as it is, what happens? Does it eventually kind of just sit there sucking in this stuff, or does it eventually spit out everything and just become nothing, or does it? What's sort of the process?
Yeah. So what happens is, we get stars continuing to die. So individual stars within the galaxies, the star's lifetime is sort of, inversely proportional to their mass. And so the bigger stars have died long ago, but the stars will continue to die and leave the lower mass stars, which are redder and redder, left over. And those can live up to something like 100 billion years. And so once we get to that point, there isn't a whole lot left. So we'll have a whole bunch of remnants of stuff, white dwarfs, black dwarfs. It'll be just a big collection of little, remnant stars orbiting around. And slowly over time, things will drift towards the black hole. It's actually pretty difficult. You have to do dynamical friction, which is a slow process. But eventually, or maybe in 1 trillion years or something like that, it'll just be in one big black hole.
Wow, fascinating. Fantastic. Romeel, thank you so much for joining us tonight. That was a brilliant talk. We really, really appreciate you joining us. And I think everybody thoroughly enjoyed that. That was a great murder mystery. So thank you so much.
Excellent.
Okay, so just before we disappear, we do have one last activity for everybody. So Romeel and Rene, as our wonderful guest speakers who have delightfully joined us and given up your time for Astronomy on Tap Edinburgh tonight, we're now going to ask you to join in one last quick game, which I'm going to do. It's not too taxing. It's not anywhere near as hard as Erica's game. She used to be a teacher, and you can tell. So it's okay.
I didn't know any of those ones.
So basically, this is a game called Arrogance. I don't know if either of you have played this game. See, look at that. He's on it already. Basically, the game is there are 3 rounds. I will show one of you a topic, and that topic is going to be space related, and there's a wild card thrown in there as well. But basically, that person then has to say how many of those they can name, and then the other person has to go higher or challenge. And you can go back and forth, like you can start low at say 2 or 3, but the second person does not get to see the topic. Only the first person gets to see it. So that's how we're going to play. So essentially what I'll do, and this is very manual, is I will share my screen in a minute and I will show you a slide. I'll ask one of you, through the magic of the internet, to look away for a minute, and I will show the slide to the other person. Then I will stop my screen sharing and I'll ask that person to name how many of those in that category they can name, they think they can name. You can start low if you want to, and then the other person has to outbid them and sort of go higher. And then eventually, if one person gets a bit nervous, they can't get any further, then you say challenge, and that person has to hit that number. Does that make sense to you both?
All right.
Okay. Yeah, that's right.
You both look extremely nervous. Don't worry. It's more likely that PowerPoint will fail, so don't worry. Okay, so Rene, you were our first speaker tonight, so I'm going to ask Romeel to go first. So, Rene, if you could just look away from your screen just for a moment. This is magic of technology. So, if you bear with me for 1 second. Okay, so can you see that on your screen, Romeel?
I can see.
Can you see that?
Arrogance. Yeah.
Okay, great. So, bear with me 1 second. There. Okay, so this is round 1. So this is your topic. So don't say anything. This is your topic. Okay. Had a thought? Okay. So, Rene, you can turn around. That was very Bond villain. I like that. That was great. Romeel, how many of that topic can you name?
2.
2. Rene?
4.
4. Romeel?
I can do 5.
Getting competitive.
Okay. Yeah, let's go for 6.
Oof.
Challenge.
Challenge. Okay, so the topic, Rene, is names of astronauts. Can you name 6 astronauts? Not cosmonauts or taikonauts, astronauts.
Astronauts. So they have to be Americans or?
No, actually, that's pretty strict ruling. You can name anybody who's technically been to
Yeah.
space will be fine.
Yeah, okay. So Yuri Gagarin, John Glenn. Then let me go with Julie Payette, Canadian astronaut. Roberta Bondar, first women from Canada in space. Chris Hadfield. Then Mark Garneau, something made all the Canadian astronauts. That's probably enough for now.
That's 6. Fantastic. Well
Wow.
done. Very good.
Way better than me. Holy mackerel. Okay.
That was impressive. Okay, so next round, Rene, you're going to start. So Romeel, if I'd like you to manually turn away from the screen, so you're not peeking, just checking he's not, not sneaking a peek. Okay, so Rene, for round 2, your topic will be.
Oh, okay.
Okay. All right. I'll give you a second just to have a think about that. Okay. Okay. So Romeel, you may turn around. So Rene, how many of those do you think you could name?
1.
Ooh, starting low.
Ooh, hard. All right. 2.
3.
Ooh.
All right, I'll go with 4.
There's a lot of nervousness around this. I'm not sure you need to be, but let's keep going. So we're at 4.
A 10 stand.
Yeah, let me think for a second. Okay, yeah, 5, yeah.
Ooh.
I think you can do it, Rene.
I think I got to try the 6. Yeah.
6. We're at 6.
Rene
What do you
gets
think,
6.
Rene?
Come on.
Yeah, I'll challenge you. So it's
All right.
so it's equal to what I had.
There's a level of fairness here that obviously exists in academia. It's very impressive.
Yeah,
Okay, so
we're
we're at 6. So Romeel, your challenge is aliens in films. Different kinds of aliens that have appeared in films. Can you name 6?
different kinds of aliens that have appeared in films.
Yes.
Well, there's of course the alien in Alien.
There you
right?
go.
That's one. Let's see. The other aliens. There was a show called. What was it called? V. Way back in the day.
Yeah.
And they had aliens who like had these, bald heads and stuff. Let's see, what other aliens do we have? Oh gosh, lots of I mean, there's Star Trek. So there's several different kinds of aliens in Star Trek. Can I name like several different, like Klingons, Romulans, Ferengi, and then and I don't know if like
we're at 4 right now, I believe. Actually, no,
okay.
5. Sorry, 5. One more.
5. Well, I mean, I it's kind of cheesy to keep going with Star Trek. There's so many of them, but Star Wars. I mean, so you could Star Wars technically they are aliens, right? I don't know, Jabba the Hutt. The Hutts are aliens, right?
There you go.
That's an alien.
There you go. I'm impressed. I thought ET would be your go-to starter, but
yeah, I don't want to make it easy,
These games are nothing.
I must confess, this was the only one I could think of initially.
It's always challenging because if you do it afterwards, you can name hundreds, but the pressure of doing it on the spot is the challenge. Okay, so we are at 1-1. We live on tension here at AOT Edinburgh. So we're at 1-1. We have one last round. So Rene, if I could ask you to turn around one more time. Okay, so Romeel, round 3.
Can I like get a lifeline for my daughter? She would know.
We'll allow extras. Yeah, we'll allow extras. Okay, so Rene, you can turn around. Okay,
All right.
as you heard from that reaction. Okay, Romeel, how many can you name?
2.
Ooh, all right.
3.
Challenge.
I'm
out.
I almost meant to challenge you at 2. Let's see what's
okay. So I told you there was a wild card. Rene, can you name 3 songs by Beyonce?
Oh dear. Oh. Yeah, it's like it's like the proximity of the blackboard kind of phenomenon.
The pressure of it.
Wasn't there one called Telephone or something like that with Lady Gaga? Or...
I will accept that, yes, even though I probably am going to get told it's wrong afterwards. But yes, I will accept that.
Yeah. What's the other one? Oh gosh. Yeah, I'm terrible with songs' name. Oh, I think I'm gonna have to fold.
Is there anybody else on the team who can name any songs by Beyonce and help Rene out? Anybody else?
If you like it, you should. Then you should have put a ring on it. If you like it, then you should have put a ring on it.
There you go. That's one. We've got 2. You should have put a ring on it.
Yeah. Oh, Single Ladies. Yeah.
Single Ladies. There you go.
There you
Very
go.
good. I think officially with that one, we can say points shared. So that was a score draw between the 2 of you. So thank you very much. Well,
Yeah,
I'm sorry for ambushing you both.
Could have chosen Metallica. That would have been. Gotten into
Astronomy and music, Beyonce goes perfectly together. But thank you.
How old is your daughter, Romeel? Is she
16.
like teenager? Okay, yeah. I was afraid it would be like something like Teletubby names or something like that initially.
Oh, I know all 4 of those. They're burned in my memory. I can't get them out. Yeah.
Well, if we do ones like, for example, Colors of the Rainbow, and then you bid like 12, then you're in real trouble.
Yeah, right.
Ultraviolet. So. All right. Well, thank you both of you so much for playing. Sorry for ambushing you at the end, but you're both great sports. So thank you very much.
Thanks, John.
Okay, so that brings us to the end of our Astronomy Off Tap event for January. Thank you everybody for coming along and watching, and for your questions and for joining in. We always really appreciate everybody for coming along and for getting involved. We always really enjoy doing these events, and we're glad you do too. I hope everybody is staying safe at home and you're keeping yourselves active and you have things to do. And hopefully this helped brighten up your Tuesday a little bit. We shall be back next month. It's always the 2nd Tuesday of the month. And if you've enjoyed tonight's event, or if you'd like to see more fun news and events that we do, please do subscribe on YouTube. You can find us at Astronomy on Tap Edinburgh. And also you can follow us on Twitter and also on Facebook as well. And as always, thanks everybody. I hope you enjoyed drinking in the universe, and we shall see you next time. Bye everybody.